Okay, so in this question, there's a combination here of different things we've got to use. We're going to use Suvat, but we're also going to use Newton's second law as well. Okay, we'll see that as we come along. So we've got this car, okay, on a journey, and it says this car is of mass 800 kilograms, okay, and it experiences, it says, a resistance to motion which is constant throughout the whole journey, okay. So they don't tell us what this resistance to motion is. Okay, so I'm going to call it R. Okay, because it's something that is trying to slow down the car. It could be air resistance, it could be friction, right? It could be anything combined there. But it does say the car is actually accelerating. Okay, so it's moving forwards in that direction under the constant tractive force of 300 newtons. So when they use that word tractive force, okay, sometimes abbreviated to that, that means the force, okay, provided by the engine, okay. So the engine is working away, isn't it? The engine's powerful, it's working away, and it creates this forward movement, okay. So that's just purely done by the engine. It's got nothing to do with the resistances then that affect the car. So it says then, determine in part A the magnitude of the acceleration of the car. Now, when you read the question, it's so important for you to see that when it says about resistance forces, okay, and the tractive force, just before each of them they say, okay, or after in the case of resistance, they say they're both constant. And if they're both constant forces, that means acceleration will be constant. Okay, if the forces are constant, it's accelerating constantly, which means then we can use Suvat. Okay. So with Suvat then in part A, well, it tells us it starts from rest. It tells over a period of 50 seconds, it reaches speed of 15. So we can get A using V equals U plus AT. Okay, so V is 15, U is 0, plus A then, which we want to work out, times T. So if you take that over to the side, you get 15, and over 50 is equal to A, because you're timesing there. Take it over, which equals to then 0.3 meters per second squared. Okay, part B then, it says calculate the magnitude of the constant resistance to motion. So basically the constant resistance to motion I called R. That's what I want to work out. So to work out R, a force, okay, or the resistance force, we need to use Newton's second law, okay. So using Newton's second law in the direction of motion, we get 300, okay, because that's the way it's going, isn't it? So 300 is the force produced by the engine. Take away the resistance is equal to then the mass of the car, which is 800, times the acceleration, which is 0.3. Okay, so using the second law there to see what the resultant force is, and then we can get R from there. So when you do maths on this, R comes out to be 60, doesn't it? 60 newtons. Okay, just using Newton's second law there. Part C then, it says when the car reaches the speed of 15, the engine is switched off and the car is brought to rest by a constant braking force. The total distance covered by the car for the whole journey is 500 meters. Find the constant force exerted by the brakes. And this question is worth 7 marks. In this one, we can use a combination of Suvat and Newton's second law, right? Because if you notice, they want the constant force, okay, exerted by the brakes, but there's also enough information there to help us with Suvat, because the force is constant, we can use Suvat. Now, it gets to a speed of 15, and then it starts to slow down. So the initial speed is 15, isn't it? That's what we're going to factor in here. But before actually we do that, let's think about what it says here. The total distance covered by the car for the whole journey is 500 meters. That's the whole journey. So I need to work out how far it's gone already. Okay, how far it's gone already. Well, remember now, we know U is 0, we know T is 50, we know V is 15, okay, so there's enough information there to work out what S is. So far, the distance S, using half U plus VT, that would be half 0 plus 15 times time, which is 50, so you work that out in your calculator. It's travelled 375 meters. That means during braking, so it's travelled 375 meters. During braking then, travels a further distance, so that its whole journey is 500, so it travels 125 meters. Okay, so now we can use SUVAT because it's braking for 125 meters. So we know with SUVAT now, it's starting with a speed of 15. Okay, it comes to arrest and it comes to stops. The final speed will be 0, and the distance covered will be 125 meters. What we need is the acceleration, isn't it? We need the acceleration. Now, there's enough information there to work out the acceleration. This is a good question because it relies upon using now another formula from SUVAT, which is this one. V squared is u squared plus 2as. So v squared is 0 squared, u squared is 15 squared, plus 2as. Well, a we want to find out, s is 125. So on the next page then, I'll say 0 is 225 plus 250a. So that means that a, well, 250a, take it over to this side, is 225. So then a is 225 divided by 250 and a minus, yeah, take it over. So you get minus 0.9 meters per second. So it's minus because remember now it's decelerating. Now, what we need to appreciate then is, okay, we can use Newton's second law to work out what this constant braking force is. So another sketch is really helpful. So we can call this braking force B if you want, okay, right? And we can use Newton's second law. So we could say, still put accelerating that way because that's the direction it's going in, but it's going to be minus 0.9, okay? So we can do it like that there, okay, accelerating this way. But it's actually decelerating, isn't it? That's the direction it's going in. However, that's not the only thing we need to consider. We need to remember as well that it's got experiences of resistance to motion, which is constant throughout the journey. Don't forget, it still experiences this resistance, R, which we worked out in the earlier part, to be 60. So, using Newton's second law, in direction of motion, in other words, the resultant force equals to mass times acceleration. Well, the resultant force, well, there's these two, but that's opposing the direction of motion, so it'll be minus 60 minus b. There's nothing going that way because the engine switched off. Okay, engine switched off. There's nothing going that way. So you've got these resistive forces due to the resistances and the braking equals to then the mass, which is 800, times the acceleration, which is minus 0.9. Okay, because it's decelerating. So if we work that out, we get minus there 720. So then B then will be minus 60 plus 720, which is 660 newtons.